In this section, we're going to learn about a new type of integral called a line integral. Now, before we do that, let's review the integrals we already know. We already know how to integrate functions over line segments. That's when you take an integral from a to b of some function f of x dx. So you're integrating over an interval on the x-axis. Right? So here's your x-axis. You start at A, you go to B, and you're integrating over that interval. All right. Then in this course, we've integrated over regions, right? Instead of just line segments. So regions, we would take it for the region. We would define some function f of x, y, and we'd integrate over the area of that region. So let's look at R. It'd be some two-dimensional object. So here's the region right there. And this is x and this is y. All right, then we've also learned how to integrate over a solid D where we have some f of x, y, z dv. So then we're in three-dimensional space. This is z, this is y, this is x. And we have some solid that we're integrating with respect to D. All right, now we want to ask the question, is it possible to integrate over a curve? And the answer is yes. Yes, it is. A curve, which is not necessarily a line segment, but it's a curved line segment. Okay, so we want, that's our goal. Let's just write this down. Our goal is to integrate over curve C, which is we are going to define as a vector valued function, which will be x of t, y of t. And if you're thinking, oh, you could expand that to three dimensions, x of t, y of t, z of t, yes, you can. But that's much harder to draw. So we're going to do this in 2 dimensions and then just kind of wave our hands at the 3 dimensions. Okay, so let's draw a picture of that curve. So the curve is here. It goes like this. It starts at t equals a, it ends at t equals b, and we have this curve, which is this vector valued function r of t. All right, so then what that means is that we have in 3 dimensions some object, some solid, which is z equals f of x, y. And that curve that we're looking at is down here, right? T equals A, T equals B. I probably have not drawn that correctly to scale, but just bear with me here because it draws better this way. And so it has a companion, right? If you will, there's a shadow up here, or if you want to think of it, I always think of it as a shower curtain, right? So I have some companion to that curve on this object that ties down to t equals a and to t equals b. And then you want to imagine it like a shower curtain between the two. And then we could say, all right, well then I want to look at one section of the shower curtain. That's supposed to be straight up and down. There we go. That's better. And that has ds, right? Some section of the arc, right? S is arc length. So it's some section of the arc is what we are looking at. It's not a dx or dy because this is a curve. It's not a straight x and y, right? Because it's curved, it's some section of the arc. Okay, so then the integral over the curve C of that function, f of x, y, is with respect to the arc of that curve, ds. And remember, S also means arc, but it also means position, right? So what we're really saying is position here, right? Which is the arc, right? Because because that's where you are situated. All right, so then remember that ds is over dt is speed. It's the magnitude of your derivative of your r function. So that means that ds would be the magnitude of r prime times dt. And that means that this line integral, right, the integral from the curve, over the curve from over the curve C of f of x, y is the same as the integral from t equals a to t equals b of f of x of t, comma y of t, then times the magnitude of r prime of t dt. Right, so this is a line integral. And you want to think about it as the integral over this curve, right? And I always imagine it like a shower curtain from the three-dimensional object down to the xy plane, right, over that curve. And we've defined that as such on the next page. So the line integral, we just derived it. The line integral, which is this integral with a c for the curve, is equal to this integral, right? From t equals a to t equals b, f of x of t, comma y of t, times the magnitude of r prime of t dt. And remember that c is your curve. So this is a little weird without seeing an example. So let's look at an example. So we want to find the line integral of xy to the 1/3 ds, right? So over that arc, over that position. Now we're given that the curve is y equals x squared on 0 is less or equal to x, which is less or equal to 1. And we know what that looks like. We've known that since algebra 1. It's part of a parabola, right? So it's going to go from 0 to 1 for the x. Therefore, it's going to go from 0 to 1 for the y because 1 squared is 1. All right, but this is no good to us as is because we need to change it into r of t form. So this curve would be r of t, and this is why we learned how to parameterize many times over in both Calc 2 and here. So the easiest way to do it is to just let your x be t, and therefore y would be t squared. And that would go from 0 is less than or equal to t, which is less than or equal to 1. And I know that I'm going to need the derivative, so I might as well find it right now. So the derivative of that would be 1 and 2t. Okay, now keep in mind, this, when you found it, this r of t, this is your x of t, and this is your y of t right here. Now, we have our function given to us right here, right? So f of xy is equal to xy to the 1/3. And that's all well and good, but that's not what I need, right? I'm going to change it over. So it's going to become the integral from t equals a to t equals b, right? So that's going to go from 0 to 1, 0 to 1, right? These are t values now. And then I'm going to take f, my function, and instead of writing x and y, I'm going to write them as functions of t. So it's very important that I know what my x and y are. But x is t. So I'm going to make it t times, and y is t squared. And that is raised to the 1/3 power. Then I'm going to multiply it by the magnitude. I'm just going to put that in vertical bars here. So the magnitude of 1 comma 2t, because that's my derivative of my position function, or my curve, dt. All right, so this is the integral from 0 to 1. This is t cubed to the 1/3. And then this is the square root of 1 squared plus 2t all squared dt. Now t to the 3rd to the 1/3 is just t. So this is the integral from 0 to 1 of t times 1 plus 4t squared. And of course, we are just going to make Maple do that. We are not going to do that by hand. And here it is. So I just tell it to take the integral. The integral is pretty straightforward, right? It's 0.848. Now, before we go any further, I wanted you to be able to see what this looks like. So the surface itself looks like this. This is what f of xy looks like, xy to the 1/3 power, right? That's not really that useful to us. Now here's the curve, but again, not great. So I drew the curve in 3 dimensions, and then I have it drawing so you can see the curtain. My scale on this object isn't great because I let y go from -10 to 10 just because I wanted you to be able to see more of the surface. But nevertheless, you're looking at one of the sections of this gray bit down here, right? So we took the shadow, if you will, that the curve and the surface, the curve has on the surface, connected it to the curve down below, and we have the shower curtain, if you will, hanging in between the two. And we integrated over that shower curtain, if you will. And that integral is right here, and it gets us 0.848. So that's your first line integral. You have many more to follow.